Okay, everybody, this is a review for Exam 2 in Astronomy 305. We've already talked about this first page, so make sure you review the types of telescope mounts and where their fixed axes point, and also the various optical pieces for the Galilean reflecting and compound telescopes. And make sure you know how to use the equations for these telescope parameters: magnification, light gathering power, focal ratio, and Dawes limit. This last one here, also known as resolving power. Then there's some calculations as we've been working on these the last couple of weeks from various coordinate systems from one to the other, like horizontal to equatorial and vice versa. So I just wanted to show you a couple of the examples and how they work out. And this is the one on page 2 of the practice exam number 2. Here it is all worked out. You can see that what you do is you first look up the planetary longitude in the appendix of your star chart of the book Stars and Planets. Planetary longitude is also known as ecliptic longitude. If you assume it's on the plane of the solar system, the ecliptic latitude is 0, and by it, I'm talking about Saturn right here. The obliquity is inclination, so inclination between ecliptic and celestial equator, 23.5 degrees. And then you use the equations in section 27 to find the right ascension and declination. And so what you're doing is converting from ecliptic coordinates to equatorial coordinates. And so here are the equations down here for that. Notice I'm finding the declination by taking the inverse sign. And it looks like everything is going to be in degrees here, so that's not really any problem. Make sure you calculate it in degree mode, and I get negative 10 degrees about right here. And then when I take the inverse tangent to find the right ascension, I put a prime on it because there might be a quadrant adjustment that I need to deal with here. Inverse tangent of all these things over there. Everything is in degrees here, so it's going to come out like that. But right ascension is always recorded in hours. So we've got to make sure that we do that, multiply it by 15 to get to the number of hours. Wait a minute, that doesn't look right. Oh, but it is. Okay, so the reason why here is that if you look at the equation alpha prime equals the inverse tangent of y over x, where y is the top thing and the bottom thing is x, we find that when you do those calculations, you find out that both of those is negative. Then you can refer to a page in your textbook that talks about quadrant. It shows that it should be actually in quadrant 3. Because I'll let you look at that figure, or I'll kind of maybe attach it to the comments of this video. It tells you need to basically convert this from being in quadrant 1 to quadrant 3 by adding 180. At that point, you get 204 degrees. Then you divide by 15 degrees to get the number of hours. It's right there. That was kind of tricky right there. All right, so then to get the local sidereal time, remember you always use your star chart, and the local sidereal time is the right ascension of your meridian. It's only the right ascension of your meridian, not of the object. So you use the date and the time to get the right ascension of your meridian. Hour angle is simply the local sidereal time minus the right ascension of the object. So this is meridian right ascension, this is object right ascension. You take the difference between the two and you found your hour angle. At that point, we can then convert from equatorial coordinates to horizontal coordinates, altitude and azimuth, using section 25 from our book. And you can see that for the altitude, inverse sine, all of this stuff right here. The only thing that I want to caution you about is this h right here needs to be converted into degrees. So it will be here in hours, and you're supposed to leave it in hours for this one. This is in hours, and that's out in hours. So right ascension, hour angle, and local sidereal time are all in hours. When you're doing the calculation, make sure you convert it to degrees when you're calculating this number, and I get 23 degrees above the horizon. So that's the altitude. And then for the azimuth, I'm doing basically an A prime. Don't really have it written out there that way. A prime. And I take the cosine, inverse cosine of all of this right here. And there's really no hours to deal with here. This is all in degrees, and then I get this angle right here. Okay, so if you look in section 25 right here, it tells you how to make a quadrant adjustment for A if needed. It basically says that if the sine of the hour angle, convert that to degrees and take the sine. If it's less than 0, you leave it alone. I was able to actually type all of this into an Excel spreadsheet. This is actually Google Docs spreadsheet. And so I even, made it so that you can type all this in. It shows you that the sign is negative, and then this right here has a conditional equation in there that if the hour angle is negative, it leaves it alone. In other words, it's basically that right there. And if it's greater than 0, then it takes 360 minus that. The rules for quadrant adjustment are all in the textbook, so you'll have your textbook with you, and you can just look in the section to figure out if this needs any adjustment. And this time it didn't. So 117 degrees for the azimuth. That's measured from north, so it should be just south of east. Okay, then going back to the Word document here, this is page 2 of the practice exam. If you go on to page 3, he's talking about looking at this star called Mirfac, and it's on your meridian at 11 p.m., and we want to figure out when that occurs. Okay, and when I calculated it, I figured out that it was around November 26. I'm going to let you go through the process of kind of backing up from that point. Here's Mirfac right here. But if I put it on November 26, this is the meridian at 8 p.m. Here is at 9 p.m., and then 10 p.m. and 11 p.m. So that's why I knew that it was around November 26 in that case, and that's what I wrote down right here. This is latitude, and then for the right ascension and declination, you can look that up in the appendix of the Stars and Planets book. Find a Mirfac, or you can simply look at the star chart, and it's called Alpha Perseus as well. Either one of those can be found in the appendices. Then you go through the process again of finding the A and the A, but this time there's no really equation involved here because it's on the meridian. So if you look at the sky dome picture here, this is the angle of the celestial equator above the south horizon, which is 90 degrees minus your latitude, roughly 58 degrees. The declination of the star from the textbook here is 49, so we add 49 onto this. That means it's going to go past the zenith. That means this is the altitude that we really need right here, which is 180 minus that amount and minus that amount right there. So this is how you find altitude if an object is on the meridian. You take 180 minus delta minus the 90 minus phi. And that's only if, if it's gone beyond the zenith. You can easily find the other equation if it's, say, south of the zenith rather than north of the zenith. Local sidereal time. In this case, the star is on the meridian, so it just so happens that the local sidereal time needs to be exactly the same as the right ascension of the star. That's because they're coincident. The star is on the meridian, so those should be the same thing, making the hour angle, which is the difference between those two, equal to 0. So star has a 0 hour angle if it is on the meridian. Going back over here to the practice exam, and this is the last question right here. It says use equations in section 25 to find the altitude and azimuth of Betelgeuse. This time it is not on the meridian, so we have to use equations rather than a diagram to locate Betelgeuse in the sky. Let's see if I can get this to zoom up a bit here. Maybe I'll have to go like that. All right, so here's the question. Betelgeuse, I use the appendix of Stars and Planets to find the right ascension and declination. Notice I'm using 5 digits past the decimal. I'm making sure this is in hours and this is in degrees right here. Local sidereal time I find from my star chart using this date and that time right there. Basically, if you look at March 22nd, you find out that that is at 12 hours of right ascension, and you're an hour and a half after that, so that's why it's 13 and a half right there. Hour angle is always local sidereal time minus alpha, which means it's the right ascension of your meridian minus the right ascension of your object. It's always that way. So positive value. A positive value means that if you're facing south, in other words, if you're at the observatory facing the glow of Walmart on the southern horizon, and you draw a meridian line up and down, this should be to the right. Because this is greater than 6, it's actually going to be below the horizon, because 6 hours of right ascension, or 6 hours in hour angle, means that it's 90 degrees, and you're beyond that. So it means it's going to be below the horizon. And so you see that I'm actually finding that out, that on March 22nd, it turns out that Betelgeuse will be 25 degrees below the horizon, and it will be basically at a point below the horizon, which is north of west. Okay, I hope this was a good refresher about how to do some of these calculations in observational astronomy. Have a good one.